This episode examines how measurement becomes the first and indispensable digital decision in water engineering. Every claim below is drawn only from the research register for this episode. Observed facts are cited, assumptions are identified. Illustrative examples are explicitly fictional and labeled as such, and recommendations are offered as engineering guidance grounded in the cited sources. Observed fact: instrumentation is foundational to digital transformation in water utilities. Suitable instrumentation improves operational awareness and enables better-informed decisions. International Water Association. Digital Water. The role of instrumentation in digital transformation. Stated assumption: digital systems cannot deliver reliable automation or decision support unless they are fed by measurement systems that meet the needs of the control and analytics processes. Arnell, Miltel, and Olson. Making Waves: A Vision for Digital Water Utilities. Water Research X, 2023. Illustrative example: consider a water treatment plant that installs continuous turbidity sensors at raw and finished water points. If the sensors are accurate and integrated into telemetry, operators can detect trends earlier. This is an illustrative example, not a documented facility. Recommendation: treat the choice of what to measure and how to measure it as the first digital design decision. Document the measurement objectives and validate that instrumentation choices map to operational and regulatory objectives before proceeding to analytics. This follows IWA strategic guidance. Observed fact: the literature links the effectiveness of automation and control to the collection, storage, sharing, and analysis of data at sufficient quality. Arnell and colleagues, 2023. Stated assumption: higher frequency sampling and better sensor specificity improve situational awareness, but they also increase data volumes and system complexity. This reflects International Water Association guidance on instrumentation. Illustrative example: a distribution network monitoring program that increases chlorine residual logging from daily manual samples to automated 15-minute readings will gain temporal resolution of events, but must also handle data storage, calibration regimes, and alarm thresholds. This is an illustrative example. Recommendation: define data quality objectives tied to decision needs, such as anomaly detection, regulatory reporting, and operational control. Select sensor types and sampling frequencies to meet those objectives, and plan for calibration, metadata capture, and validation steps as part of the instrument lifecycle. This follows IWA strategic transformation guidance. Engineering trade-off: sensor selection. The trade-off is precision and frequency versus cost, maintenance burden, and volume of data for downstream processing. The literature emphasizes that sensor capability should be chosen to satisfy analytics and control needs, not vice versa. Observed fact: telemetry and data pipelines convert sensor outputs into operational awareness when data are reliably transmitted, stored, and made accessible to analytics and operators. This is described in IWA publications. Stated assumption: operational awareness requires not only raw telemetry, but also processing layers that cleanse, contextualize, and visualize data. Simple telemetry alone is insufficient for proactive operations. Illustrative example: an operations center dashboard that fuses flow, level, and pump power telemetry produces a view of efficiency and hydraulic state, enabling operators to spot inefficiency sooner. Without pre-processing, noisy telemetry can create false alarms. This is an illustrative example. Recommendation: build telemetry architectures with explicit data hygiene steps, time synchronization, metadata tagging, validation routines, and clear contracts for data consumers. Specify provenance and uncertainty for every data stream before using it for control or automated decision-making. This follows IWA strategic guidance. Engineering trade-off: centralized versus edge processing. Centralizing raw telemetry simplifies analytics and governance, but increases bandwidth and latency requirements. Deploying processing at the edge reduces data movement and can improve resilience, but adds device complexity and maintenance burdens. The academic literature links both approaches to outcomes and emphasizes matching architecture to operational needs. Observed fact: automation, models, and control applications can make water facilities more proactive, provided the underlying data and models meet the required fidelity and are deployed to address actual regulatory and service needs. This is supported by IWA Publishing and Arnell and colleagues, 2023. Stated assumption: closed-loop control should be implemented only where measurement confidence, actuation reliability, and safety governance are verified. Otherwise, decision support and supervised automation are preferable. Illustrative example: a supervisory control routine that modulates aeration based on dissolved oxygen sensors can reduce energy use when sensors are reliable and actuators respond predictably. If sensors drift or actuators fail, automatic control can create harm. Hence, staged deployment with human-in-the-loop oversight is prudent. This is an illustrative example. Recommendation: adopt a phased approach. Begin with decision support tools that propose actions, log operator responses, and validate model predictions. Move to partial automation only after demonstrated model performance, documented failure modes, and governance for overrides. Embed test harnesses and post-decision monitoring to detect model degradation. This follows IWA transformation guidance and the work of Arnell and colleagues. Engineering trade-off: automation level. Higher automation can improve response speed and consistency, but reduces human oversight and can amplify errors if underlying inputs are flawed. The literature recommends aligning automation level with data quality and regulatory risk appetite. Observed fact: the reviewed materials identify governance, security, and clear operational requirements as essential complements to instrumentation and analytics in digital water systems. This is described in IWA strategic publications. Stated assumption: expanded telemetry and remote actuation increase the attack surface. Governance must therefore include risk assessment, access control, and incident response planning tailored to water sector priorities. Illustrative example: a distributed sensor network that exposes application programming interfaces without proper authentication may enable unauthorized writes to set points or the injection of false telemetry, causing inappropriate operator response. This is an illustrative example. Recommendation: integrate cybersecurity and governance requirements from project inception. Define who can change measurement or control logic, require authenticated telemetry channels, audit trails for decisions and overrides, and periodic reviews of failure modes and response plans. These are consistent with IWA strategic recommendations. Engineering trade-off: security versus availability. Strict security controls can limit rapid operator response and complicate remote maintenance. Lax controls increase vulnerability. Governance must strike a calibrated balance that preserves safety and service continuity. Observed fact: digital twins, artificial intelligence, and models appear in the literature as powerful tools, but their effectiveness depends on the fidelity and provenance of input data and clarity about application scope. This is discussed in IWA Strategic Digital Transformation material and by Arnell and colleagues. Stated assumption: models are simplifications and will have limits of validity. Using them beyond their tested domain risks misleading decisions unless model uncertainty is quantified and communicated. Illustrative example: a hydraulic digital twin calibrated on dry weather flow data may not accurately predict pollutant transport during storm inflows unless the calibration dataset includes relevant transient events. This is an illustrative example. Recommendation: treat digital twins as decision support artifacts with explicit statements of scope, calibration regimes, validation metrics, and uncertainty bounds. Include continuous validation using new telemetry and plan for model retraining or recalibration after significant process or instrumentation changes. Engineering trade-off: model fidelity versus manageability. More complex models can represent system behavior more closely, but demand more data, more compute, and harder verification. The literature recommends model choice guided by the decisions they support, rather than maximal fidelity per se. Observed fact: the literature presents a strategic view. Successful digital transformations begin with instrumentation and data capabilities, proceed to analytics and automation phased by need, and always align with service and regulatory requirements.
Stated assumption: every utility has different constraints, including budget, skill, and assets. Therefore, implementation sequences should be tailored rather than copied verbatim. Illustrative example: a prioritized sequence might start with critical measurements that resolve the highest value operational questions, add telemetry and data hygiene, introduce decision support for one process, then expand. This is an illustrative approach, not a prescriptive schedule. Recommendation: Implementation and Decision Framework. Use a simple decision framework derived from the reviewed materials. First, identify decision needs. What operational or regulatory decisions will change if better data are available? Second, define data quality objectives tied to those decisions: accuracy, latency, frequency, and provenance. Third, select instrumentation and sampling strategies to meet those objectives, including lifecycle costs for calibration and maintenance. Fourth, design telemetry and processing that preserve uncertainty and metadata and enable audit trails. Fifth, deploy decision support with human-in-the-loop oversight and validate performance before escalating automation. Sixth, embed governance, cybersecurity, and continuous validation into the program plan. This framework is intentionally generic, so each utility can adapt it to local constraints and regulatory obligations. Observed fact: across the reviewed sources, trustworthiness depends on demonstrable measurement quality, transparent model limits, validated automation behavior, and governance processes that include security and accountability. This is described in IWA publications and by Arnell and colleagues. Stated assumption: stakeholder trust is gained through evidence, calibration records, uncertainty quantification, incident logs, and clear governance, not only through attractive visualizations or claims of digital maturity. Illustrative example: a utility that publishes sensor provenance, calibration histories, and model validation tests will enable regulators and the public to assess system trustworthiness more readily than one that publishes only derived performance indicators. This is an illustrative example. Recommendation: require demonstrable evidence of data provenance, calibration regimes, model validation, and documented governance before certifying automation for safety-critical functions. Maintain transparent audit trails and scheduled reassessment intervals as part of the operational contract. These are consistent with IWA strategic recommendations. Engineering trade-off: transparency versus operational sensitivity. Transparency supports trust, but may expose operational details that utilities consider sensitive. The reviewed literature suggests structured disclosure: provide provenance and validation evidence without exposing exploitably detailed asset maps. Narrator: digital water is not an off-the-shelf magic. It begins with measurement decisions made for specific operational needs. The sources assembled for this episode converge on a simple engineering axiom: you cannot automate what you cannot measure to the fidelity required by the decision. From sensor selection and data hygiene, through telemetry and operator workflows, to models and control, each layer must be designed with the next in mind. The engineering trade-offs, cost versus fidelity, centralization versus edge processing, automation level versus oversight, security versus availability, model complexity versus manageability, are not theoretical. They are the practical levers utilities must balance. The implementation framework offered here is deliberately decision-focused. Begin with decisions, specify the data those decisions require, choose instrumentation to meet those requirements, and only then build analytics, models, and automation with governance and validation built in. This sequence aligns with the strategic and technical arguments in the IWA and academic literature, and provides a defensible path from measurement to trusted automation.
This narration is constructed strictly from the 3 sources recorded in the episode research log. Where examples are used to illustrate concepts, they are explicitly labeled as illustrative and do not represent documented case studies. The episode remains evidence-limited by the scope of those sources. Further applied case studies and facility-level data would be required to produce site-specific technical prescriptions or to satisfy the research log's open gates. Closing engineering reflection. The practical test of a digital water program is not the number of sensors, dashboards, or algorithms it installs. The test is whether the program improves a defined decision while preserving safety, traceability, and the ability to recognize uncertainty. A reliable sequence starts with the question, identifies the evidence required, verifies the measurement chain, and introduces automation only when operators and governance can supervise its limits. In that sense, Digital transformation is less a purchase than an engineering discipline. Measure deliberately, validate continuously, document what is known, and keep the system adaptable as conditions change.